So when we left off in the last video, we had just figured out how we can take one given factor, divide it out of the original polynomial expression, and take the depressed polynomial and factor it. But what are we going to do when we aren't given any factors or any clues? Well, then we're going to have to rely on a few other skills that we're about to learn in this video that will help us come up with that missing factor that we could divide out. One thing that we need to remember is the fundamental theorem of algebra, which says that every polynomial equation with a degree greater than 0 has at least one root in the set of complex numbers. Similar to that is the corollary that says that if it has a degree of n, then it's going to have n roots, including repeated roots. So over here on the right, let's start with this one. Notice the polynomial equation is cubic. Its highest degree is 3. And notice that it crosses 1, 2, 3 times. Not all cubic equations will cross 3 times. Notice this is also a cubic equation, and it crosses once, and then it touches its tangent to the x-axis here. That creates a root of multiplicity of 2. That can happen. Roots can have multiplicity of 3. Consider the equation y equals x cubed. Think about what that graph looks like. It looks like it only crosses once, but this is a root of multiplicity 3 based on the corollary to the fundamental theorem of algebra. Right here we have a quadratic. Notice that it crosses twice. But as you know, we have studied quadratics in the past, like this one, where it doesn't cross at all. It still has 2 solutions in the complex number system, but they're going to both be imaginary, if you recall. And that can happen. But let's take a look at what these polynomial equations look like in factored form. Notice, looking at the graph, I could write the factors. I know that it crosses at 4, so I get x minus 4. And then I know that it touches when x equals 1, so I write that root twice to write the equation. That's just one possible equation that would go through these 3 roots. Same thing here. I know that my roots are 2 and 3, so my factors are x minus 2, x minus 3. That's how I could get back to that original quadratic. Alright, so let's solve an equation and state the number and type of roots. So the first method that we can use is just finding that greatest common factor, pulling it out, and then using the zero product property. Notice that I looked at 6x cubed and 3x, and I said, okay, well, what do they have in common? They have a greatest common factor of 3x. When we factor that out, this is what we're left with. We have here things multiplied together. That's a factor, and this is a factor. Anytime you have something grouped together in parentheses, that makes it a factor. So we set each factor equal to 0 and solve. We get x equals 0, x equals plus or minus I square root of 2 over 2. Notice we were expecting 3 answers because it's a degree 3, and that's exactly what we have here. We have 1 real root and 2 imaginary roots. Go ahead and pause the video and try the first one. This is a pretty basic factoring of a quadratic. We just break it apart. We set each factor equal to 0 and get negative 7 and 3, which means we have 2 real roots. Sometimes, though, we're going to have complicated expressions like you see here, where it's not going to be very easily factored. And that's when we're going to pull in Descartes' rule of signs as well as the rational root test. Descartes' rule of signs says, I'm scrolling back up in the notes, that if you have a polynomial with real coefficients and the terms are arranged in descending powers of the variable, like standard form, the number of positive real zeros is going to be the same as the number of changes in the sign of the coefficients of the terms, or less than this by an even number. And the number of negative real zeros is going to be the same as the number of sign changes when the coefficients use the variable p of negative x. So this doesn't mean a whole lot as we read through what Descartes' rule of signs is, but it's important to have this in our notes because hopefully once we go over it, you'll be able to look back and say, oh, I understand what it was saying up there. So let's try it in an actual example. Here we have p of x equals 4x to the fourth minus 3x cubed minus x squared plus 2x minus 5. It is in descending order. The degrees keep going down, 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 down. So we're going to look at this and go from the first term to the second term. 4 is positive, 3 is negative. So that's one sign change. Then I go to the next term, negative 3x cubed to negative 3x squared. Negative to negative, that's not a sign change. Then I go from negative x squared to positive 2x. That's a sign change. And then finally, from positive 2x to negative 5 makes another sign change. That means that I don't know what the zeros are here, but I could have 3 positive real zeros because there are 3 sign changes, and then you keep subtracting 2 until you can't anymore, or 1 positive real zero. So if I had had 7 sign changes, then my answer would be 7 or 5 or 3 or 1. If I had had 12 sign changes here in this polynomial, my answer would be 12 or 10 or 8 or 6 or 4 or 2 or 0. You keep subtracting 2 until you can't any longer subtract 2. I can't take away 2 from 1. I would end up in the negative answers. All right, so now we have to figure out, well, how many negative real zeros would there be? So the first thing we have to do is compute p of negative x. So notice I'm taking out x everywhere that I had an x in my original polynomial. I'm taking out x and I'm replacing it with negative x. Now we need to simplify. If you have a negative raised to the 4th power, negative times negative times negative times negative is positive. So my first term simplifies to 4x to the 4th. And it doesn't change. What happens here if I have a negative raised to the 3rd power? Negative times negative times negative is negative x cubed times negative 3 makes positive 3x cubed. Again, I'll put it off to the side. I have a negative 3 times a negative x cubed. That gives me a positive 3x cubed. All right, negative x squared. That means negative x times negative x, which is positive x squared. So my next term is positive x squared. My next term, 2 times negative x makes negative 2x. And then finally, negative 5. So now we're able to look for some sign changes. Going from the first term to the second term, no change. From the second term to the third term, no change. They're both positive. Going from the third term to the 4th term, we have a sign change. And going from the 4th term to the 5th term, no change. So that means there could be 1 negative real zero. Now we have to consider the imaginary zeros. And the way we're going to figure those out is by the process of deductive logic. Notice the highest degree here was a 4. So we are expecting 4 zeros based on the fundamental theorem of algebra. So I'm going to put total here on the right. The total needs to be 4. Then I'm going to put positive. Then I'm going to have a column for negative. And finally, a column for imaginary. All right, think back to our combinations. We could have had 3 positive. We could have had 1 negative. That would leave 0 imaginary because 3 positive and 1 negative, there's no room for any imaginaries. That's one option. I could have had 1 positive, 1 negative, and then I could have had 2 imaginaries for a total of 4. The goal is to get a total of 4 every time. So these are my only combinations because I would always have 1 negative real 0, and then positive could be 3 or 1, and depending on how many positives there are dictates how many imaginaries there would be left. So we would say that this polynomial could have 3 positive, 1 negative, or this polynomial could have 1 positive, 1 negative, and 2 imaginary. Think about what that would look like, that second situation. It might cross in the negative and in the positive, something like that, and then some imaginary. All right, let's try another one. Let's try the number 5 together, shall we? So looking at positive sign changes, that's 1, negative to negative, negative to positive, positive to negative. So there could be 3 positive or 1 positive. Next, I'm going to rewrite this, but everywhere I see an X, I'm going to take it out and put parentheses. And then I'm going to go back and put a negative X in each of these parentheses. Negative raised to an odd power stays negative, so I have negative 3x to the 5th. Negative raised to an even power becomes positive, but there's a negative out front, so I still have negative x to the 4th. Negative raised to an odd power is negative. There's a negative out front, so it becomes positive x cubed. Negative x squared becomes positive. And finally, negative 5 is a constant. So looking at my sign changes now, no change, 1 change, no change, another change. So I could have 2 negative or 0 negative. Because remember, you can subtract 2 until you get back down to 0. So putting this into a chart form, number of positive, negative, imaginary, and our total. What should our total equal? It should equal 5. All right, let's put our combinations together. We could have 3 positive, 2 negative. That doesn't leave any room for any imaginaries for a total of 5. We could have 3 positive and 0 negative, which leaves room for 2 imaginary. I could have 1 positive and 2 negative, which leaves room for 2 imaginary. Or I could have 1 positive, no negatives, which leaves room for 4 imaginary answers. The imaginary numbers will always come in pairs, always. We'll get to that in the last part of our notes today. So knowing the signs of the zeros is very helpful when we're predicting what our zeros could be, but equally helpful is using the rational root theorem. The rational root theorem is a great way to come up with a list of possible rational roots for your polynomial function. It's not the only way, but it's a great way. basically you're going to take the constant right here and you're going to look at the leading coefficient over here and you're going to just make a ratio of their factors. So all the factors of -3 would be 1, 3, -1, -3. Those all, you can divide -3 by all 4 of those numbers. And all the factors of 6 would be 1, 2, 3, 6, also -1, -2, -3, and -6. So that's where these lists of factors come from. And when we make a ratio of them, we get this list of numbers. This is actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possible numbers. But it's really helpful because then you just have to run some of those numbers through synthetic division to end up with a depressed polynomial. Let's try to find one factor of this polynomial. We're trying to find one of these possible roots that solves this equation, and we're going to use synthetic division to do it. Let's start with the number 1, shall we? We put 1 here, 6, 8, -7, and -3. I bring down my 6, I multiply, get 14, subtracting 7, and 1 doesn't work because I didn't get a remainder of 0. And again, I'm going through my synthetic division rather quickly, but you too will get really quick at it after you practice it a little bit. Bring down the 6 times -1 combined with 8 times -1 makes -2, which gives me -9 and +9. -1 doesn't work as well. So I go back and I try the next one. I'm going to skip ahead to 1/3. I'm going to bring 6 down. That makes 2. 2 combined with 8 is 10. That makes 10/3. Right away, I'm seeing I don't think this is going to work out. I mean, I can get my calculator and verify, but I have a bad feeling. So I'm going to just stop with that one and try the next one. Let's try -1/3. When I bring down the 6, I get a -2. Combined with 8 gives me 6, which makes another -2. Combined with -7 makes -9. Times a -1/3 is a +3, and we have a winner. So now I know x plus 1/3 is one of the factors, and my remaining polynomial is right here, 6x squared plus 6x minus 9. This I could factor. I know I can pull out a factor of 3, so I have 3 times the quantity, 2x squared plus 2x minus 3. And while I might not be able to factor this, I could use the quadratic formula to find the other 2 remaining factors at this point. Let's try that with, let's try number 6. All right, so if I use Descartes' rule of signs, no change, no change, no change, no positives, I'm not expecting any positive zeros. So now I'm going to put in -x everywhere I had an x. This gives me -x cubed plus x squared minus 9x plus 9. So now I'm expecting 1, 2, 3 negative zeros, or 1 -0. Remember, I should have a total of 3, so I might have 3 negative, or I might have 1 negative with 2 imaginary. So that means I'm going to take my list of possible rational roots, and I really only need to check some of the negative ones because of Descartes' rule of signs. So looking at my constant here, it's 9. and my leading coefficient is 1. So I'm taking all the factors of 9, 1, 3, and 9. Those are all numbers that will divide into 9, and I'm dividing by all the factors of 1, which are just 1. And remember, we want the positives or the negatives. So these are all possible numbers I could try in my synthetic division now. Let's start with 1, shall we? In my coefficients, 1x cubed, 1x squared, 9x, and 9. Bringing down the 1. One does not work. Positive 1 does not work. Let's try negative 1. Just going to erase. Goes a little bit faster that way. And I have an answer. Now remember, I really didn't need to start with positive 1, did I? Because I know I don't have any positive roots, so that was kind of silly. But in the interest of practicing synthetic division, it does kind of reaffirm that we're probably on the right track. So negative 1 is one of my roots. That's one of them. So I'm going to put it up here at the top. X plus 1 is one of the factors. Remember, I have a depressed quadratic now. If I fill in, this is 1x squared plus 0x plus 9. What I literally have left here is x squared plus 9. My original polynomial could be rewritten as x plus 1 times x squared plus 9. We already solved this one. We know that means x equals negative 1. But when we set this piece equal to 0, we subtract 9 from both sides. X squared is negative 9. Taking the square root, x is plus or minus 3i. So my answers are negative 1, 3i, and negative 3i. So it ended up being this combination. But do you see how we used Descartes' rule of signs and the rational root test to come up with these answers? That's what we're going to do for all of these problems. We'll continue to practice some of these in class, but for now I'm going to scroll down to our very last concept. Suppose a and b are real numbers with b not equal to 0. If a plus bi is a 0 of a polynomial function, then a minus bi is also a 0. What that means is kind of what I alluded to earlier, that the imaginary roots always come in pairs. You're never going to have 2i as a root if his little partner, negative 2i, isn't right along with it. You might have 5 without having negative 5, but that's because 5 is a real number. If you have an imaginary or a complex number, you're always going to have the conjugate along with it. So if we're trying to write a polynomial function of least degree, this one is going to at least be x cubed, because there are 1, 2, 3 zeros, 3 roots that were given. This one, they only give us 3, but we know that we have to add the other imaginary partner here, which is negative 2i. So this one's going to be at least x to the 4th. And right here, we have 0, negative 5, and 3 plus I. That seems like 3, but remember, we also have to have 3 minus I. So what does this look like? That's going to be to the 4th degree again. Let's go ahead and write these zeros as factors. Negative 4 would become x plus 4. Negative 3 would become x plus 3. And 5 will become x minus 5. Now I can FOIL or box. It really doesn't matter how I do it. I'm going to just FOIL these two binomials. X times x gives me x squared, 3x. Take away 5x is negative 2x. And then finally, 3 times negative 5 makes negative 15. Next, I probably would want to box this to get my final answer. So I'm going to go out into my margin here, x plus 4 boxed with x squared minus 2x minus 15. Gives me x cubed minus 2x squared minus 15x, 4x squared minus 8x minus 60. So altogether I have x cubed plus 2x squared minus 23x minus 60. That would be my final answer for a polynomial with these roots, these zeros, with integral coefficients. That means my coefficients have to be integers. Let's take a look at number 14. So if I take each one of these zeros and put it into factor form, I have x minus 0, x plus 5, x minus 3 plus I, and x minus 3 minus I. Because remember, to change it into factored form like we did here, we just changed the signs because we're doing x minus the root. So we're doing the same thing over here. This is pretty simple. It's just x. This is x plus 5. But let's take all of this and multiply it first. So I'm going to first simplify these parentheses. That gives me x minus 3 minus I. And my second one is x minus 3 plus I. Now there's a variety of ways you can handle this. I like to just do a 3 by 3 box because I think of it as a trinomial times a trinomial. So x minus 3 minus I times x minus 3 plus I. And as I go through my box, I can do it pretty quickly to come up with all of these numbers. Negative 3 times negative 3, negative 3 times negative I times x, negative 3I, and finally negative I squared. Remember from unit step 13, I believe it was, negative I squared is just, I squared is negative 1, there's already a negative, so this just equals 1. Also, you can note that ix and negative xi, those cancel out. 3i and negative 3i cancels out. So altogether from this box, I'm going to be left with x squared minus 6x plus 9 plus 1 makes plus 10. So now we have x times x plus 5 times x squared minus 6x plus 10. Just distributing, that gives me x squared plus 5x times x squared minus 6x plus 10. And again, going into the box method, this is going to be a 3 by 2, x squared minus 6x plus 10. Look, we're getting that 4th degree we were hoping for. Coming back out of the box, we end up with x to the 4th minus x cubed minus 20x squared plus 50x as our polynomial. Now that one was a lot harder than number 12, but it's the same method. You just keep multiplying the factors together until you get one polynomial with integral coefficients.